Welcome back, AP Stats. This is the fourth and final installment of Chapter 3. We're going to be talking about the mean. In our last lesson, we talked about the median, quartiles, and interquartile range. Now we're going to talk about another measurement of center and spread, the mean, and the measure of spread, the standard deviation. We'll talk about that near the end of this lesson. All right, so let's talk about the mean. We're going to consider a set of data values, and we're going to call this whole set of numbers y. All right. We're going to let n be the size of the data set, or the number of values in the data set. So the set is called y, and it has n values in it. All right. Then the mean of y, which we call, what do you call that? Well, that's called y bar. All right. Y bar. That can be written as y bar, the mean of the set of data values. Y is the sum of those data values divided by the size of the set. In other words, we find the sum of the data values and then divide by the number of data values. That is the definition of the mean. Your calculator can do this very easily in one variable stats. So we'll be going back to that. Try it for the set of data you use to make the box plot. That's the data on the kids catching the bugs. So we'll work with that in our calculators and then we'll move on. All right, so we're back to the calculator. Just as before, we go into stat and into edit and enter the data if you have not done so already. I already have. So now we're going to do one variable stats. We're going to go to stat and then over to calc, and then we see item number 1 is 1var stats. We hit enter. List is list 1, very good. Frequency list, doesn't matter. Hit calculate. And the first thing that pops up is our mean, which is 22. If you recall, that's actually the same as the median, and that is not intentional. The mean and the median do not have to produce the same value, and I'll let you think about why that's true. But 22 is the mean in this context. All right, let's talk about the significance of the mean. What does the mean mean? Well, when we calculate the mean, what are we calculating precisely? We're calculating the one number that, if it were substituted for all the data values, would produce the same sum. It's a one number representative of the data set, specifically regarding its center, right? What is the mean? We saw that 22 was the mean of our data set. That means that if I replaced all 25 of those values for the numbers of bugs those campers caught, if I replaced every one of those values with the number 22, it would have the same sum. So 22 is, in a sense, a one number stand-in for each data value. It's a one number representative, if you will. And that's why it's a good measure of center. Number 2, we are calculating the balancing point of the data set. And we have a histogram right here that demonstrates this principle well. This is the earthquake data. This is not the bug data, of course. This is the earthquake data. And like the bug data, our mean is very close to where our median is. All right, they're very close to each other. We have this little scale fella right here that you'll see in your textbook. This picture is taken right out of your textbook. And you'll see that this point right here, if we were to stick this right here, we could balance the histogram as it were. Right? So we have an arithmetic and a geometric way of understanding the mean. Cool. Mean versus median. This is really important to master as soon as possible. The AP test loves to make sure that you know when to use the mean and when to use the median. Okay? So let's talk about it. The median is preferable to work with sets of data that are strongly skewed. If we were to look at a histogram of data for which the median would be ideal, they would be left or right skew. Okay? Data are skewed when a few high or low values pull the mean up or down respectively. All right? The classic analogy I use for this is the curve breaker. So you're in a tough class and you take a tough test, but then there's that one or two set of students who are going to succeed regardless of what everybody else does, and their scores pull the average up. So the teacher looks at the average and says, oh, it looks like the students generally knew what to do. No, it was just the curve breaker. That is an example of a right skew distribution, couple high values, pulling the mean up towards them, okay? So skewness is common when there is a clear boundary at one end. Test scores are a good example of this, 0, or if we're talking about final passing grades, 60 or 59.5 technically, is the lowest possible passing grade. So you have a boundary on one end, but no clear boundary on the other. In theory, you could get a score above 100 perhaps, right? Incomes are bounded by minimum wage, for example. So there is a clear left endpoint, but no clear right endpoint for wage. And that is why income is an example, and one of the go-to examples, in fact, of a right skew distribution. The mean, however, has more statistical applications. That is the understatement of the day. The mean and its partner in crime, the standard deviation, are probably the two most important calculations in all of statistics. Actually, scratch that. They are the two most important calculations in all of statistics. Which one's more important? Silly question. They're both equally important, all right? The mean has more statistical applications by a lot than the median. It's usually preferable, though, for symmetrically distributed sets of data, which happen very often, interestingly. It is not uncommon for data to be symmetrically distributed. That's not just something that happens every so often. That's very, very common. And there are some instances we'll talk about this year where it is guaranteed. That's kind of wild. But it doesn't matter what kind of data you're talking about, a bell curve is guaranteed. That is possible. We'll talk about that later, much later. Right? One example, really any meaningful measurement that you would have at a doctor's office is going to be somewhere along a bell curve, all right? You have a lot of people who are average height, some people who are especially tall, some people who are especially short. This is an Olympic year. We get to see all the really tall people playing basketball and all the really short people doing gymnastics. So they are at the extremes of the bell curve, but most of us, like probably you and me, are somewhere in the middle. All right, so the mean is a good measure of center for something like height. For a symmetric set of data, the mean and the median, interestingly, should be at about the same place. And I'll let you think about why that's true. All right, let's talk about the mean and the median when interpreting a set of data. All right, we're back to the unsinkable LOL Titanic. All right, the distribution of ticket prices is skewed to the right. Yeah. The mean, 33, what is that? That is British pounds, is substantially higher than the mean, than the median of 14.4 British pounds. All right. The higher prices at the right have pulled the mean toward them and away from the median. Now, let's see how that happens in our graph. Where the blue turns to this orange color over here, that is the dividing line marked by the median. All right, if we were to count to the middle, the median price would be between 0 and 20 pounds. All right, but these really expensive tickets over here, those are pulling the mean in their direction. Okay. And so here is my balancing point, which marks the location of the mean. Okay, so the mean is getting pulled by these high values over here. The mean is more influenced by skewness. All right, so in this case, the median would be a better measure of center because the data are highly skewed, and the mean is more affected by skewness than the median. More with mean versus median. You want to summarize the expenditures of 500 credit card company customers and have looked at a histogram. Here is that histogram, of course. You have found the mean expenditure to be $478.19 and the median to be $216.28. Which is the more appropriate measure of center and why? Well, this question comes down to only one point. Is this a bell-shaped curve or is it strongly skewed? And especially if you consider these data out here, which may well be outliers. Well, that's definitely an outlier, but some of these may be outliers as well. If you consider the length of the tails and the fact that we have a corgi tail on one side and some other kind of tail on the other side that's significantly longer, this is a strongly skewed distribution here. So whenever the data are strongly skewed, as we could see in a histogram, we go with the median. $216.28. That is a better measure of center because it is less influenced by skewness. The mean, as we see here, is heavily influenced by skewness. It is quite far from the median, so we should go with the median on this one. All right, another really important slide here. Let's look at the mean, median, and mode on the big three distributions. Let's start with the distribution in the middle. It's titled normal or no skewness. However, the generic term for a curve like this is unimodal, one mode, and symmetric. All right, in that situation, the mean, median, and mode are right here. All right. Now, this is in the context of a histogram, okay? So we would have vertical bars increasing in size and then decreasing in size. So the tallest bar is right here. That's why this x-axis value would constitute the mode, all right? It's where the bump in the data is. This would also be where the median is and the mean, all right? It's the middle of the data and it's a one number representative of the data. So it's a median and a mode respectively, okay? So let's look at this negatively skewed curve. We would call it left skew, all right? Left skew. The mode is going to be where the bump is, all right? So the mode is going to be this value, okay? And then we have the median and the mean. Now, what's going on here? Well, the mean is more heavily influenced by skewness, all right? And by influenced, I mean it's further from the mode, okay? So if we have a lot of data values down here, the mean is going to be strongly influenced by these data values being in the mix. The median doesn't really care about what's going on down here. And I'll let you think about why that's true. But the median is not as heavily influenced by the skewness of a set of data, all right? If we are counting to the middle, as it were, ordering the data values from least to greatest, there's a couple of really big values. Well, they are no better or worse than any other value. If we count to the middle, the median is a little off-center relative to the mode, but it's still pretty close. The mean is heavily influenced by these really low values, right? Same going on here. We have the mode, which is right at the bump, and then the median is a little bit to the right of the mode, and the mean is heavily influenced, all right? Heavily influenced by the skewness of the curve, by these high data values that pull the mean upwards more so than the median, right? A way that I like to think about this, you just forget about this if this is not helpful. The mode, obviously, it's where the bump is. It is the class that is most frequent, all right, in your data set. The mean is mean. It likes to be angry and alone and stays far away from the mode as possible. And the median is middle, median, middle, right? So that's a good way of thinking about it. Maybe if you're into mnemonics like that, you have the mode here. The mean is mean. I don't like any of you. And the median is somewhere in the middle. Maybe that'll help some of you. Maybe that's cringe. I don't know. Moving on. Summarizing symmetrical distributions. We're talking about standard deviation now. Up to this point, we've talked about measures of center in this lesson. Now we're going to be talking about measure of spread. So just like in our last lesson, we talked about quartiles and interquartile range, we had this idea of interquartile range as a measure of the spread of data, okay? and it was a nice outlier detector as well. Standard deviation is like that, except it takes the idea of a mean and runs with it. Okay? Like the mean, the standard deviation is useful for describing symmetrical data sets. Where the mean measures the center, standard deviation measures the spread of a set of data, how variable the data are. Remember, statistics is all about variation. This is the best measure of variation in cases like this, where the data are pretty much symmetrical, which happens a lot. The standard deviation can be understood as the average distance, that is deviation, of each data value from the mean. Now, I use this word loosely, that's why I put quotes around it. A deviation can be positive or negative. A distance is only positive, all right? The standard deviation can be understood as the average distance of each data value relative to the mean. So some data values are close to the mean, some data values are far from the mean. But how far is a data value on average from the mean? That is the standard deviation, all right? I just use the word deviation here because it's in the phrase standard deviation, all right? Just trying to make that connection. A deviation is technically positive or negative. If you look it up, a distance is always positive. It's a scalar. That probably mattered to maybe one of you. Moving on. Computing the variance in standard deviation. Deviations can be either positive or negative, as we said. So if we just found the average deviation, values above the mean in our data set would cancel out values below the mean if we were to add them up and divide by the number of values. That would not help us find the spread of the data. That'd be kind of silly. So statisticians found a little trick, and it's not maybe what you would expect. I'll be honest, when I first learned statistics, what I expected statisticians to do is say, oh, well, let's just find the absolute value of all the deviations and average those. But no, statisticians have something different up their sleeves. We first compute the average squared deviation of the data values from the mean, and we call that the variance. So the average square distance is this guy right here. We say take each data value, subtract the mean, square it, and keep doing that for all the data values. Y is a stand-in for a data value. We subtract the mean of all the data values, and we square it. All right, so we're finding square deviations. All right, so then we add all of those squared deviations together, and then we divide by the number of values minus 1. What's the minus 1 coming from? Turns out, and I'm going to say this periodically this year, that minus 1 is beyond the scope of the course. The reason why it's not just n there, right? Honestly, I don't even know. The rabbit hole goes very deep on that one, surprisingly. So we're just going to leave that there. Maybe someone in the comments will enlighten me. I don't know. But this would be the S squared is the average square deviation. Now, since we have the average square deviation, it makes sense that if we square root this value, we have the average deviation that's no longer negative. That squared has a property of making positive this difference right here. So if I have a data value that's above or below the mean, I square it, it becomes a positive number. I'm summing a bunch of positive numbers and dividing, so I'm going to acknowledge all of those deviations as positive in a sense, right? And once I take the square root, that is my standard deviation. So this bad boy right here is the typical measure of spread that we will use, the standard deviation. And gratefully, you have graphing calculators that can do this without you having to compute a single square root, you lucky ducks. All right, and that's what we're going to be doing right now. We're going to be computing the variance for our bug catching data. Here we go. Okay, here we go. Bug catching data, still there. We enter it into edit. Very good. go to stat, go to one variable stats. We're used to this. Go down to calculate, and here we go. So we have our mean, we have a couple of sums, and then we have S sub x. All right, S with a subscript of x. That is the standard deviation. All right, you'll notice there's a number very similar to it right below. This is a Greek letter sigma subscript x. These numbers are very similar. They are different enough that I need to acknowledge this right now. Sigma sub x for this class and for basically every statistics class you're going to take, unless you are a super duper duper nerd, is absolutely useless. S subscript x is your standard deviation for your variable x, which is the only variable you're using. You're using one variable here. The calculator refers to it as x. All right, so the standard deviation for that set of data that we denote the variable x is this number right here. Sigma x, forget it exists. Okay, it's useless. Standard deviation, useless. So this is more of a comprehension question. Want to make sure you understand what standard deviation refers to. It is a measure of spread. Let's see if we can apply it. Company is selling a new smartphone, and it advertises that the phone's battery has a mean lifetime of 5 years. Cool. If you were in charge of quality control at the factory, would you prefer that the standard deviation of lifespans of the batteries be 2 years or 2 months? And why? Take a moment, think about this one, unpause the video when you want my take. All right, you've unpaused the video and you're trusting me with my take. I would definitely go with 2 months. Here's why. If I want my mean lifetime to be 5 years, do I want to be on average 2 years off? Yeah, you have a lot of people who get a lot of life out of their phones. But on average, if people are 2 years off of this 5-year mean, that's a massive spread of the data. It would not be surprising if people's battery died in 3 years, and you get a lot of nasty phone calls from their, I guess, new phones, because they wouldn't be using the ones that died. Anyway, if it's only off by 2 months, that's a significantly shorter period of time. So if our phone batteries last 5 years on average, and they're only an average of 2 months off of that mean. So how far is each battery going to go relative to the mean? Well, some go a little less than 5 years, some go a little more than 5 years, but on average, you're only about 2 months off. That's much better. That's predictable. People know what they're buying. It's better all around. All right. Describing quantitative data. There's an acronym we want to keep in mind when we are dealing with quantitative data. And at a Christian school, this may be surprising, but in statistics, I'm going to teach you how to cuss. What? We want to talk about C, the center. We refer to the median or the mean, whichever is appropriate. We talk about the median when data are strongly skewed, and the mean when data are symmetric. Unusual features. If I have outliers, if I have multiple bumps in the data, multiple modes, I want to acknowledge those sorts of things. Shape. Is it uniform? Symmetric and bell-shaped. Unimodal and symmetric. That's a synonym. All right? Left skew, right skew, bimodal, multimodal. Talk about the shape of the data. And finally, the spread of the data, what we've been talking about most recently. Talk about quartiles and interquartile range if you have data that are strongly skewed, or standard deviation if you're talking about data that are symmetric. All right. So just like we talk about the mean with strongly skewed data, the median, with strongly skewed data, we talk about quartiles and interquartile range with strongly skewed data when speaking of the spread. If we're talking about the mean, our data should be symmetric, and then we'd also use standard deviation. So that is how we cuss in statistics. Maybe not what you were thinking, but the shock value of it all will help you remember. When you see quantitative data, the best thing to do right at the beginning is cuss. Talk about the center, unusual features, shape, and spread. All right, one last note. This will be helpful for your homework. Parameters versus statistics for mean and standard deviation. A parameter, if you recall, is a measurement about the population. All right, that's everyone that you could possibly be studying. So if you're doing a study on the number of bugs that all students catch, the true mean for all possible students you could study would be a parameter. If you wanted to choose a sample of 25 students, like we did in this section, and we were to find the mean of that, that would be a statistic. So 22 bugs on average, that is a statistic, okay? So parameters talk about the population. Statistics are measurements that speak about the sample, okay? So most of the time, not all the time, parameters, measures of the population, use Greek letters, while statistics, those are measurements of the sample, use Roman letters. For example, if I'm talking about the sample mean and sample standard deviation, I would use X bar for the sample mean and S for the sample, that should be sample, standard deviation. These are Roman letters, X and S. We use them to talk about sample stuff, sample mean, sample standard deviation. If we're talking about the population, then we would use mu, all right? This cat right here is Mew. If you are a fan of a certain anime involving pocket monsters, then yes, you are familiar with Mew, but this is a different Mew, all right? Sigma, this we've mentioned before. This is the population standard deviation, okay? So mu refers to the population mean, sigma refers to the population standard deviation, okay? That's going to come up in the homework. It's also going to come up in your packet that you're going to be doing. Very good. So just wanted to get that out of the way. And speak of the homework, here is the homework. Have fun with this. And you're going to get some opportunities to cuss. So very good. You got something to look forward to there. Have a great day.